Dear students, so in this class, now let us discuss a new research. So the theorem which states that letter K following K, F following CLXY. CLXY means set of all compact linear map from X to Y. Then KF and if GF plus G are following CLXY, where G also following, where what about G? G is again following GF and G. G also following CLXY. This is our first result. Let K following K, F and G following CLXY. CLXY means set of all compact linear map from X to Y. KF, then we have to show that this KF and F plus G are following CLXY. So in previous class we were discussing about when F is in CLXY means F is a compact linear map only when for any open ball U following X, F of U closure is a compact subset of Y. That's our definition. So to prove KF following CLXY, so let proof is let secant xn be a bounded sequence in X. Secant xn be a bounded sequence in X. That means for some alpha positive, no xn strictly less than alpha. Okay, and also F following CLXY. Also, it is given F following CLXY. Since F is in CLXY, in previous class we were discussing that when F is in CLXY, then sequence if x and j be a sequence in X such that F of x and j which converges in Y for any sequence x and j in X. F of when x and j be any sequence in X, then f of x and j converges in Y. Why? Because of the result that we were discussed in previous class. Okay. Since f of x and j converges in Y, we know that for any scalar k into f of x and j also converges in Y. When kf of x and j converges in Y, then in the light of the previous arguments, in the light of the theorem which we discussed in previous class, then we know that kf is also following CLXY. Kf is also a compact linear map. So the first part is finished. How to prove this f and g? F and g, then when f and g fall in CLXY, the next part is when f and g fall in CLXY, then we have to show that f plus g also fall in CLXY. So its proof is, suppose g fall in, f is also fall in CLXY, g also fall in CLXY. G also fall in CLXY means there exists a subsequence Zj of the sequence x and j. What is x and j? X and j be a subsequence of which one? X. X and j be a subsequence of X. Let Zj be a subsequence of X and j. Since G fall in CLXY, then clearly G of Zj, G Zj converges in where? Converges in Y. This is again by using previous arguments. Since G fall in CLXY, we can find out a subsequence Zj of X such that G of Zj converges in Y. Then this Zj be a subsequence of X such that f of Zj also, since Zj be a subsequence of X, then we know that f is in CLXY, so for f of Zj also converges in where? X. Since Zj be a subsequence of X and f fall in CLXY, then by the previous arguments we have f of Zj also converges in where? F of Zj also converges in Y. G of Zj converges in Y f of Zj converges in y, that means f of Zj plus g of Zj, that means f plus g of Zj which converges in y. F plus Zj converges in y means clearly f plus g fall in where? F plus g fall in Cl. So finished. This is our proof. Okay. So the proof is heavily depends upon the theorem which we discussed in previous class. Agreed? Okay. So this is the first theorem. Now consider another result. Let f fall in k or let f fall in CLXY. The next theorem states that let f fall in CLXY, g fall in CLYZ, g fall in CLYZ. Then one of them is when f fall in BLXY, not CL, when f fall in BLXY and g fall in BLYZ, f is a bounded linear map from x to y, g is a bounded linear map from y to z. Then, and one of them is compact, either f or g. Either f or g is compact, means either f or g fall in CL. So either f or g is compact, then gf fall in C, then gf, the product, then gf fall in CLXH. So this is an important result. Let f be a bounded linear map from x to y. G is again a bounded linear map from y to z. That is x and y are any two non-linear spaces. F is a bounded linear map from x to y, and G is a bounded linear map from y to z. Then their composition, G composition f or GF. GF is a compact linear map from x to z whenever one of this f or g is compact. So how to prove this one? That's our second result. So to prove this one, let secant xn be any secant in x. Secant xn be a secant in x. So suppose it is bounded such that now xn less than alpha for some alpha greater than 0. Agreed. Then if f fall in, suppose f is a compact linear map, it is given f is a bounded linear map from x to y, and we can assume, or the condition imposed that one of them, either f or g, is compact. Here we assume that f is a compact linear map from where to where, x to y. So by the first result that we already proved in previous class, when xn is a bounded sequence in x, f is in CLXY, then there exists a subsequence xnj of x such that f of xnj which converges in y. Okay, which converges in y. Now what is g? But g fall in BLYZ. G fall in BLYZ means g is a bounded linear map. Since g is bounded, surely it is continuous. Then by the continuity of g, since g is continuous, then g of, since f of x and j converges in y, g is continuous, then g of f of x and j also converges in where? Also g is from where to where? G is from y to z, so it converges in z. G of f of x and j converges in z. Okay, so listen, if f is in CLXY and f of g is in BLYZ, then the continuity of g ensure that g of f of x and j converges in z. G of f of x and j converges in z means this g of f or g composition f fall in where? CLXH. So finished. Then if g fall in CLYZ, what happens there? Suppose g instead of f fall in CLXY, suppose g fall in CLYZ and f is in BLYXY. What happens there? Again, since g fall in CLYZ, there exists a bounded sequence in y, such that is y and j, such such that g of y and j converges in such. Okay, so g of y and j converges in such. F of xn is a bounded sequence in y, then g of f of xn converges in such. In that case also, gf fall in CL such. Agreed? So clearly, so the theorem is immediate. Agreed? Okay. Now, another important result. Now let us discuss another important result. The result is, let y be a Banach space. Let y be a Banach space. Y be a Banach space. Fn fall in CLXY. Fn is a compact linear map from where to where? X to y, where x and y are number spaces. Here also y is a Banach space. F is in VLXY. F is a bounded linear map from where to where? X to. F is in VLXY. And norm Fn minus f tends to 0 as n tends to infinity. Then as n tends to infinity. Then we have to show that f fall in CLXY. Then f fall in CLXY. This is an interesting result. X and y are non-linear spaces. Also y is a Banach space. Fn is a compact linear map from x to y. But f is only a bounded linear map from x to y. If norm Fn minus f tends to 0, means norm Fn minus f less than some epsilon, then f is also a compact linear map. When Fn tends to f, that's the crucial point. When y is a Banach space and Fn tends to f, when Fn fall in CLXY, then f is also a compact linear map. How to prove this one? So, the proof is again heavily depends upon the theorems which we discussed in previous class. That is, the proof is this way. To show f is in CLXY, our aim is to prove f is in CLXY, means f is a compact linear map from x to y. How to prove this f is a compact linear map? To prove, in order to show f is a compact linear map from x to y, we have to show that f of u is a totally bounded subset of y because of the result that we already proved in previous class. Okay. So, to prove f is in CLXY, that u fall in x, u is an open ball in x, then to show that f of u is totally bounded. F of u is a totally bounded subset of y. This is our requirement. How to prove this one? Listen, it is given norm Fn minus f tends to 0 as n tends to infinity. Okay. So we choose a epsilon positive such that norm Fn minus f strictly less than some epsilon by 3, where n equals 1, 2, 3, etc. Okay. Right. But what is Fn? Fn, it is given Fn fall in CLXY. Fn is a compact linear map from where to where? X to y. Fn is a compact linear map from x to y. Since Fn is a compact linear map from x to y, then for any open ball u fall in x, clearly Fn u is totally bounded. Fn u is totally bounded subset of y. Since Fn fall in CLXY, Fn u is totally bounded subset of y. Agree. Hence, there exists some x1, x2, etc. xn fall in u, such that since Fn is totally bounded, then Fn of xi or Fn of u, Fn u, which is a subset of Fn u is a subset of union j ranges from 1 to m Fn xj epsilon by 3. Union J ranges from 1 to n, open, it's an open ball. Union, S. Since Fn is totally bounded, then Fnu is a part of union J ranges from 1 to n, open ball, Fn xj epsilon by 3. Sure. Why? Because of this argument. Since Fn fall in CLXY, U is an open ball, then Fnu is a totally bounded subset of Y by the previous arguments. Then, in the light of this statement, when Fn of U is bounded, totally bounded subset of Y, we can find out some Xi's in U such that Fnu is a part of union J ranges from 1 to n, or Fn xj epsilon by 3. Some xj's. We can find out some xj's in U which satisfies this condition. Agreed. For x fall in U, then there exists some xj. There exists some xj in x such that Fn of x, since as it is Fn of x is a part of union J ranges from 1 to m, union J ranges from 1 to m, and or Fn is a part of open ball, Fn xj epsilon by 3. Okay, Fn xj epsilon. There exists some, we can find out some xj's in U which satisfies this condition. Then for some x fall in U, there exists some xj such that Fn x is a part of open ball, Fn xj epsilon by 3. Fn x is a part of open ball, Fn xj epsilon by 3 means, or Fn x fall in this one, that means norm Fn minus norm Fn x minus norm Fn x minus Fn xj, that is strictly less than epsilon by 3. Okay, that's its implication. Now consider norm fx minus f of xj. Norm f of x minus f of xj. Norm f of x minus f of xj can be rewritten as it is norm f of x minus Fn x. That is norm f of x minus Fn x plus Fn x minus Fn xj. Norm f of x minus Fn x plus Fn x minus Fn xj plus Fn xj plus Fn xj minus f of xj. Okay. You can introduce minus Fn x plus Fn x minus Fn xj plus Fn xj simultaneously. So which is less than or equals norm f of x minus Fn x, that is norm f minus Fn into norm x. One step is missing, skipping there, plus norm Fn x minus Fn xj. Norm Fn x minus Fn xj means, yes, norm Fn x minus Fn xj strictly less than epsilon by 3. Epsilon by 3 plus norm Fn xj minus f of xj, that is norm Fn minus f into norm xj. Okay. So it is strictly less than, what is norm f minus Fn? Norm f minus Fn is strictly less than epsilon by 3 plus, here it is again epsilon by 3 plus norm Fn minus f is also strictly less than epsilon by 3. What about the norm x? X fall in where? X is in U. What is x in norm xj? Xj also fall in where? Xj fall in x means, or xj fall in U. Xj fall in U. X fall in U. Xj fall in U. That means, what is U? U is an open ball having a radius 1. What is U? U is nothing but set of all x fall in x with a norm x strictly less than 1. So U is an open ball having radius 1. Therefore, when x fall in U, norm x less than 1. When xj fall in U, norm xj less than 1. So it is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 equals epsilon. That is, norm f of x minus f of xj strictly less than epsilon. That means f of, what is x? X fall in U with the norm f of x minus f of xj strictly less than epsilon means f of u is a part of, that means f of u is a part of union j ranges from 1 to m, open ball f of open ball f of xj epsilon. Open ball f of xj. Okay, since x of order u, then the norm f of norm f of x minus f of xj is strictly less than epsilon. That means f of u is a part of union j ranges from 1 to m, open ball f of xj epsilon. So that means f of u is, that's a conclusion, f of u is totally bounded. F of u is totally bounded means, that is what we require here. To prove f is a compact linear map from x to y, then for any open ball u fall in x, then we show that f of u is a totally bounded subset of y. Clearly, f is a compact linear map from where to where, x to y. That is what we require here. Okay, thank you.